Let's start with a high-level review of what a neural network is. A neural network takes a set of numbers as inputs and calculates a set of numbers as outputs. In this example, the inputs are hours of sunlight, millimeters of rain, and average temperature in a growing season. The outputs are crop yield of corn, wheat, and oats. One way we can train a neural network is by examining a large number of example inputs and outputs. These examples are used to determine weights for connections between the inputs and the outputs that, on average, best match the examples. We'll examine this learning process later, but for now, let's focus on the math of a trained neural network. We can multiply sun, rain, and temperature by a set of learned weights and then sum up the results to get our corn yield. We can then repeat for wheat and oats. To satisfy neural network experts, I'll note that I'm conveniently ignoring that we can also learn a bias. This is a distracting detail that can be treated as just one more weight for an input with a constant value. In this simple example, all inputs and outputs are numbers, and we're making an implicit assumption that all other factors impacting crop yield are constant or irrelevant. I've killed almost every plant I've owned, so there's a strong probability that this isn't the best way to model crop yield. But it still works as a nice, simple example. This starts to hint at the fact that a big part of data science is organizing appropriate data in an appropriate format to feed into the model. We're going to set aside this important aspect of data science because for the time being we're focused on how neural networks work. While predicting crop yield is nice, it's likely more useful to predict the best crop to grow based on weather in a given region. So we can extend our neural network to incorporate a hidden layer. A hidden layer is just a layer that isn't an input or an output. We're also going to adjust our output to a probability that corn, wheat, or oats is the best crop. A probability is a number between 0 and 1, while our multiply and sum operation yields a number that's unlikely to fall in that range. This means we have to perform some nonlinear transformation to get from arbitrarily large positive and negative numbers to values between 0 and 1. Nonlinear mappings are operations that can be applied to the result of each sum product operation at each node in our network. With this set of inputs, we can really only determine highest crop yield. So we likely want to extend our model with information about the value of each crop in a given region. Now our hidden layer is also an interim step in reducing the dimensionality of our network. Why don't we just feed the price of corn into the node that had previously calculated corn yield? We could adjust our network to do this, but then we're biasing our network to learn in certain ways. Engineering a network by connecting the output of one trained network to the input of another to take advantage of known relationships is called embedding. We're going to defer how we deal with categorical, non-numerical inputs, like the name of a region, and just say for now that there's a way to do that.